Hello, everybody. My name is Ali Aga, and today, with several members of Team CoSTAR, we are presenting an overview of the CoSTAR team solution at DARPA Subtraining Challenge, with a focus on autonomy in extreme environments. Here is our team website, where you can find more information, videos, papers about our solution and technologies we have developed for this competition. The talk is going to be divided to three parts. First, I'll go over our team structure and our concept of operations. In part two, we'll discuss the timeline and strategies of robot deployment at different competitions that we have participated. And in part three, we will go deeper into various capabilities and some selected modules of our overall autonomy framework. So there's a large theme behind the results we are presenting today. Over the last 3 to 4 years, more than 100 people contributed to our solution as software stack. Team CoSTAR is a collaboration between several institutions, mainly JPL, Caltech, MIT, KAIST, and LTU, as well as collaborators and interns from several other schools and sponsors from various industry partners who are listed on our website and can find all the details about the team structure there. First, I'll start by why NASA is part of this challenge. In general, subsurface voids or caves are important and interesting targets in planetary exploration, because if there are signs of past life or present life in other planets in our solar system, caves and subsurface voids are one of the most likely places to find those, because caves have the potential to shield and harbor life from cosmic rays, from extreme temperature variations on the surface of other planets, and harbor life on, for example, Mars or other rocky bodies in our solar system. In addition, caves provide a natural shield for potential future human exploration missions and astronauts, and can protect astronauts from cosmic rays and temperature variations on other planets. So for these reasons, and among others, caves are interesting targets for NASA, and there are studies, investments, and research to explore Mars analog and planetary analog Mars-like caves on Earth. So the picture you see here is one of our efforts to deploy multiple robotic systems to explore Mars-like caves on Earth for autonomously for hundreds of meters. This is a test in Lava Bed National Monument in the border of California and Oregon, in a set of caves that will resemble and are analog to what we might potentially see on Mars. The goal of these missions, again, are explore these caves in search for targets such as the ones you see at the bottom left that are interesting for scientists and are potential signs of life. So with that broad interest in exploring extreme environments and subsurface voids, we entered DARPA Subtraining Challenge as it was very well aligned with the goals and capabilities that NASA and JPL requires for such missions. So the goal of DARPA Subtraining Challenge is to explore various types of underground environments, man-made, natural, and mixed, autonomously, and where we don't have prior information about the environment, and environment is unknown. It's challenging from many different aspects. From perception side, there's no GPS. Communication is pretty challenging in these sorts of environments due to non-line of sight operations, And mobility-wise, there are a lot of mobility stressing elements in this class of environments. Operationally, also, this is a challenging problem as robots potentially need to explore long paths and cover larger spaces without any prior information about the environment. No human is allowed to enter the course, and only one human supervisor can see the data coming from inside the course and robots if and only when communication is established with the human supervisor. And there is a 1 hour time slot that each team can conduct their run and send the robots to explore this environment and collect the information. The scoring mechanism is based on finding objects that DARPA has distributed in the environment. There are 20 or 40 objects, depending on which run we're talking about, have been distributed in the environment with different signatures, visual or signatures, or you can detect them based on gas sensing or based on wireless radio signal sensing and so on. And each team gets 1 point per artifact if the robots can get to that artifact, find it, classify it, and locate it with less than 5 meter error, meaning you map the environment, find the location of object, and communicate that to the surface within that 1 hour mission time. CoSTAR concept of operation is based on deploying multiple robots with complementary capability. Complementary capabilities from the locomotion sense, meaning some of them have legs, some wheels, some flying systems, and also the robots are heterogeneous from the sensing and computation perspective. They have different sensors, different levels of computational power on them. We try to create a wireless mesh network close to the entrance of the cave to be able to maintain communication with that single human supervisor outside the course. As you see, the blue dots here represent the communication nodes that robots drop like breadcrumbs to create that wireless mesh network. And the red dots are robots that can be in communication with the operator or can leave the mesh network and carry out the mission autonomously and come back to return the data to the operator when the certain conditions are triggered or when close to the end of the mission. Here is a brief summary of the different robots we have deployed in various competitions in the last 3 years. We have deployed legged platforms, wheel systems, rovers, tracked robots, as well as drones and rollercopters. Okay, with this brief overview of our concept of operation and some of the robots we have deployed in the competition, in part 2, I will be talking about our deployment strategy at different competition and how it evolved over time, and some of the lessons we have learned during this process. This effort has been a very heavy effort on the field testing side. So we have been field testing our effort at more than 20 different field sites across the country, and during the last 2 to 3 years, we have had more than 150 days of field testing in real world environments with hundreds of kilometers exploration on our robots. In terms of timeline, the effort started in 2018. We had the first STIX event at Colorado. Then to prepare for the tunnel competition in mines, we conducted a lot of tests in California as well as West Virginia in coal mines. You see a picture here from a coal mine 900 feet underground in West Virginia Arch Mine. Then 6 months later, we participated in the urban competition to prepare for the urban competition. We have been testing in various construction sites as well as the urban structures and close to competition in Washington at local sites next to the competition venue. Then we had a gap due to COVID where we did not have lab access or robot access, but before few months before the final competition, we gained access again to our robotic systems and started to conduct heavy field testing, this time at Kentucky in limestone mines to align our development with potential assumptions that we have had about the final competition structure. Throughout our developments and deployments, one overall big lesson we learned was on managing risk versus complexity in deploying these autonomous robotic solutions. SUBT was pushing development both in the direction of advancing capabilities and algorithmic abilities of these systems, as well as product readiness, that you have a system that you deploy and it just works. While the ideal point to be is on top right, where you have high levels of autonomy, advanced capabilities, and system is very resilient and has low levels of risk in deployment. In real world, there are constraints induced by resources and define a Pareto curve that one needs to decide what is the best trade-off between risk and complexity on this curve. So for our team, this is how this trade-off evolved over time. In tunnel competition, we had certain levels of autonomy with certain level of risk. In urban, as we had more resources and time, we increased the autonomy while we stayed almost in the same level of risk. For the mixed event, we pushed a lot more on the autonomy and capability side, while we increased a little bit the risk in the deployment. We selected these target trade-off points based on our assumption of how the course might look like. And after the competitions, looking back, this would have been maybe the ideal trade-off points for our team. In tunnel and urban, our assumptions were pretty close, and in final, in mixed environment, we have been targeting our practice runs much larger environments that had implications on our hardware choices, communication system, as well as algorithms for global planning, artifact detection, SLAM, and so on. These assumptions shape the performance of the robotic team in various deployments in the competitions. They helped us to win the urban challenge, and they helped us to rank 2nd and 5th in the tunnel and mixed environment. As you see, those trade-offs are reflected in solution complexity of that increased over time for our team, as well as the level of risk we took in deploying these solutions over time. In the next 2 slides, I will share videos that highlights some of the robots and technologies we have deployed in these competitions. Here is our first video from the tunnel and urban. This is the staging area where our team deploys and sends the robot in. After they pass the start line, they're in communication only with one person, human supervisor. This is the viewpoint from the human supervisor screen. And as robots go into the course, the additional robots try to daisy chain, and while we are close to the entrance of the course, they try to maintain the communication with the supervisor. As they enter and explore, they create a 3D map of the environment in real time, and they do so in a multi-robot fashion. You see the points that the map jumps. These are the rendezvous points, or the points that two map has overlap, and the Islam solution aligns them and creates a unified map. This happened in urban, in multi-level scenarios, going up and down the stairs, and of course, in the course, we need to handle variable lighting as well as challenging traversability situation. This is a short clip from one of our tests at Arch Mine, 900 feet underground in a coal mine, where the robot is assessing the surface traversability and tries to decide where the wheeled robot can traverse, or when a tracked robot needs to go to handle higher level slopes, or if there are stairs, dispatch the legged platform to handle the stairs and explore a multi-level environment. At the backbone of these coverage behaviors, there's a concept called IRM, Information Roadmap, that creates a graph that captures the connectivity of the free space, and that helps these sorts of behaviors in that the robots go into various rooms or different parts of the course, different dents in the mine structure, to search for the artifacts distributed by DARPA, to find them and report them to the surface. Of course, in all these competitions, we deployed a multi-robot solution, and robots were coordinating with each other on exploring different parts of the course to maximize the coverage efficiency. Some of these multi-robot behaviors need to be tested offline in simulation environments before we deploy them into the field. Here you see a snapshot from our artifact detection system in urban and tunnel, where in the right the semantic targets are selected and sent to the operator alongside their confidence and type. This is our communication node deployment system that drops nodes like breadcrumbs closer to the entrance of the course to create a wireless mesh network and increase the reach of the operator. But still, the robots do leave the communication range. Here you see a case where a robot was out of communication range for 20 minutes or so, and when it comes back to the communication range, it sends back the map and the artifacts it has collected data for during the run. Sometimes when a robot is stuck or we need a communication using a drone, we deployed our flying systems. This is a video from a test in a mine in West Virginia, that the drone is searching and covering different part of this coal mine and returning back to the operator to send the data back for further analysis. And this is the roller copter concept that I mentioned earlier, that in the first year of competition, we studied and invested on this mobility platform that rolls on the ground and fly when needed to increase the operation time of traditional drone systems. And here is a video of the run of day 2 in the mixed event. We picked day 2 as it was a day that the system was deployed fully with no calibration issues at the beginning. A bottom right video shows the world and exploration from the perspective and front camera of one of our legged platforms walking and moving in the environments. Top left is the internals of the algorithms, where you can see the map that is being created and the IRM information roadmap, the graph that's being created that captures the connectivity of the space and what is explored and what's not. As you can see, the other robots are also in the mission, and the robots, when they reach, get to each other, they dispatch themselves to different parts of the course to efficiently cover the space. In this round, we deployed 5 robots, 3-legged platforms, 1 wheeled and 1 drone. The robot you see in this video traversed about 600 meters across 3 different domains: tunnel, urban, and cave in 24 minutes. And overall, the entire team together explored about 1.6 kilometer in total, and detected and scored 11 artifacts in the first 20 minutes of the mission during this run. Bottom left graph shows kind of how the artifacts scoring times evolved over time, and in the first 20 minutes how it increased, and the next graph next to that shows how this particular robot that you see in this video, its traversal distance increased over time, almost linearly after its deployment, which was almost 6 minutes into the mission. Here, this part of the video shows the perceptually degraded part of the course, where the robot falls down and actually stands up and continues the mission in fog and smoky type environment. And I believe this is the extent of the space that the robot reaches before we run out of time in this 30-minute run of the final event. In terms of numbers, in our best runs throughout the last 3 to 4 years, here are some of the quantitative measures that we achieved. In terms of the versatility and modularity of our autonomy solution that is called Nebula, we were able to integrate it on 14 different types of robots. In terms of the traversability and navigation, in our best runs, we were able to traverse about 2 kilometers with a single robot in extreme environments, and map about 4 kilometers of those environments. From a networking perspective, we were able to deploy 35 nodes in our best runs, covering several kilometers of distance and space, maintaining communication between robots. And from the multi-robot deployment perspective, in our best runs, we were able to achieve 11 robot deployment, 4-legged, 4-wheeled, and 3 drones. But on average, we deployed in the last year about 4 to 6 robots on typical practice runs. And from the perspective of machine learning, we made a lot of progress throughout the years, and in the final event, we were able to detect and report all and score for all the artifacts that we saw in the course. These modules come together and integrated in an overall autonomy framework that we call it Nebula, in a coherent manner. In the rest of the talk, we will go a little bit deeper into each one of these modules, but I start the part 3 of the talk by giving an overview of the overall architecture of Nebula and how these modules are connected to each other. So here's a simplified view of the Nebula architecture. So there are 5 different types of modules here: planning modules in orange, perception modules in green, world belief in purple, communication blue, and belief prediction in red. At the bottom, you see Agent 0, or our base station. And at the top, you see agent 1 to N representing each robot in the team. Different robots in the team, as well as the agent 0, are connected via our wireless mesh network. So the blue blocks here that represent hardware and software associated with our networking part of the solution. The orange part is the planning and control part that generates the command that is being sent to the physical robot or simulation environment. And then we receive measurements from the sensors that go into the green part, the perception module of the Nebula framework. Perception and planning modules share information via the shared world belief across different modules and different agents. And the red part is responsible to forward project the state or belief over the states into future to look at potential outcomes and help active perception type behaviors to control the sensory information. Examples are when we are running coverage algorithms, these modules help us predict and understand how to move so that we maximize the coverage and better see the parts that are more uncertain in our map, or look at certain parts of the terrain in a way that we reduce the traversability risk and be able to go through narrow passages, narrow doors, and challenging parts of the course. More details about the architecture and the framework can be found in this paper. And a really key part of this architecture is to build and try to study and build sort of representations that can be predicted in a computationally tractable way to allow for that resiliency in the algorithm and being able to handle uncertainty better. So in the rest of the talk, we will go over some of these modules to discuss them in more depth. So I will hand it over to our team members to discuss those modules.
All right, in this slide, we are going to talk about the estimation pipeline that was used in Team CoSTAR during the DARPA challenge. You know, estimation is a challenging topic in robotic community. Each environment may bring down the performance of the sensors. For example, in underground environment, we don't have a good GPS, or in perceptually degraded environment, like in a fog or smoke or dust, the camera or LiDAR may fail. So our desired state estimation needs to not only be robust and resilient in those environments, but also provide a continuous and a smooth output with real-time performance. So basically, resiliency is a key factor in state estimation. You know, in recent years, there has been a tremendous amount of research done in order to make a robust state estimation from multiple odometry algorithms. The main goal of the resiliency is to use multiple sensing modalities and estimation methods. And once the failure is detected, we simply see redundancy in each individual sensor or methods. As you can see in the right figure, we have different sensing modalities, including LiDAR, camera, IMUs, and so on. And we have different estimation methods coming from those sensors, like wheel inertial odometry, WIO, or VIO, vision inertial odometry, and so on. So here we are presenting our robust solution to have a basically resilient state estimation. Our solution is called HERO, or Heterogeneous Resilience Odometry Estimation. In HERO, we have three main layers, as you can see in this block, namely sensing modalities, estimation methods, and multiplexing block. Here, basically, HERO selects the best source of odometry and the best is defined by the user. In sensor layer and estimation method layer, we have internal health check, depending on the number of sensor and estimation methods. And we constantly check the diagnostic messages coming from the health check report. And we reinitialize the odometry upon receiving any failures. You guys can go ahead and read this paper here for more detail about the hero structure. But here we are basically we briefly touch on what hero is doing in order to handle uncertainty. These are the example of uncertainties such as gap, divergence, or jump. In hero we have different confidence check criteria. For example, the message timeout that detects the gap, or covariance of the estimation error for detecting the divergence, and so on. So the right table shows how the hero is switching between the estimation methods if they fail, and sending out the odometry to other modules until all methods die at the same time, which is a very rare case and won't happen, I guess. Yeah, this is how hero is working in terms of the resiliency logic. Please go ahead and read this paper here for more detail about or development on hero. But here we can show a simple implementation of hero on our Boston Dynamics spot. For the cell estimation, we use two main estimation methods in hero, namely LiDAR inertial odometry, which is basically this method is developed by the SOPTI team. It's called Locus, and Boston Dynamic Vision Inertial Odometry. And user set LIO as the best source of odometry for the hero. So hero selects LIO until LIO fails. Here you can see hero is robust when either LIO or vision inertial odometry fail, and the cost map looks clean in the right side. While in the case that we only use LIO and we don't basically have any hero or no resiliency, when hero is fail, the cost map gets noisy, and you can see it in the right bottom plot. Thank you.
My name is Ben Morell, and I'll be talking about CoSTAR's SLAM solution. But I wanted to start by going over a bit of the context of the challenges that we're trying to solve with SLAM. And in particular, we're interested in our global SLAM solution. So imagine you have a team of robots, and I want you to explore this underground environment here. It's a map of a limestone mine, Kentucky underground. And it's very large in scale, long distances to explore, many different pathways through this whole maze. And when you send your robots through this environment, I want you to tell me where my backpack is, for instance, that I left somewhere in the mine. And I want you to tell me to within 5 meters. But each of these pathways is also very large. This is what it looks like inside, multiple car widths wide. And so exploring through this, you're going to be covering a lot of distance. Let's say you send the first robot out and it goes and explores like this, covering a lot of ground. Send out the second one, it covers different areas but crosses paths sometimes. And you continue to send out the robots, exploring a lot of different areas and covering, in the end, kilometers of distance. And so what we're building up to for CoSTAR is having 8 robots, many kilometers of total traverse length, and we still want everywhere along those paths for every robot to be accurate to within 5 meters. On top of that, when we're looking at the SLAM challenges, you can see there's lots of crossing over of robot paths and thousands of loop closure possibilities there. And these are the challenges that we're trying to tackle with our global SLAM solution. Our SLAM solution is called LAMP, Large Area Mapping and Positioning. And the key features are that it's a centralized multi-robot SLAM approach. It uses outlier resilient post-graph optimization, leveraging GTSAM. And we have a prioritized method of calculating loop closures. This is the architecture diagram. And if we start off with each of the robots, we begin by taking in an odometry source, such as from Hero. That is used to build a post graph where we're looking at odometry edges. We also add in IMU and artifact information. And every 2 meters, we add a scan from our point cloud that's adaptively filtered for the environment. So it can be similar for different types of robots. That pose graph and scan information is sent back from every robot to the base station. In the base station, that's where we look for multi-robot loop closures, and we do our robust pose graph optimization, and then send back the updated global graph to each robot. Now, this architecture for multi-robot is very beneficial in that it brings greater accuracy to that multi-robot team. That's the core benefit. However, it brings many challenges with it as well. One of them is, how do we compute loop closures accurately and efficiently? How do we address the challenge of false positives and make sure it's not going to corrupt the overall solution if you have one bad loop closure? And then finally, scale, both in the distance traveled, the number of nodes in the graph, the complexity of the number of robots is a real challenge, and that also increases the chances of false positives. So we tackle this in a few ways. The first way for loop closures is using a few different techniques in a LiDAR-based loop closure. We use adaptive proximity to search for nearby nodes, where the radius of search increases as our uncertainty in position increases. And we use artificial beacons, radio beacons that have been deployed as markers of having visited a location that either the same robot or other robots have visited before. These detections of loops are then going through a process to compute alignment that accumulates nearby scans for more density and then uses some outlier resilient initial alignment approaches, such as teaser++, before doing GICP. And the loops that pass through there then get added to the graph. But how we set this up and how we tune it is a little bit different in that we want to make sure we absolutely do get loop closures that are real. And so we allow many loop closures through. But this means we allow many false positive loop closures. Hence, we rely on a robust postgraph optimization that is resilient to outliers. This is the central part of LAMP as well. We use something called graduated non-convexity. It's an algorithm that is robust to up to 90% outliers, and that's integrated through GTSAM and Chimera RPGO. And this is our robust postgraph optimization approach. To give you a bit of an idea of how powerful this tool is, let's look at a map here. On the left is from Prelim Run 2, different colors of different robots. And you can see some of these white lines are potential loop closures that are clearly false positives. They're matching, they're aliasing between different disparate areas. But the map looks fine. These have been handled in GNC, they've been rejected in the optimization. If we turn off outlier rejection and just take the loop closures as is, it's an absolute miss. So we can see what we're able to handle there with GNC. The final part is tackling scale. And again, we're in a centralized approach and we can leverage that to our advantage. We're looking at the scale of how do we handle many loop closures. And we do that through a few methods. First is prioritization based on observability. So that's looking at the observability of the point cloud for the 2 candidates that we're closing the loop, and then ranking potential loops based on that observability. We also prioritize based on a loop batcher that looks at the structure of the overall graph and picks a subset of potential loop closures that, if solved, will maximally improve the error on that graph. These then go through into a queue that is computed in a parallelized loop computation approach before it goes into the optimization. Using this architecture really advanced what we're able to do, giving us 6 times more throughput in loop closures, the number of loop closures we got, as well as a 45% reduction in the overall error of the multi-robot graph. So some examples of large-scale results in different tests. On the left is a test where we had one large loop for a single robot, where it traveled maybe 1 kilometer without any loop closures, and then it was able to have one loop closure to correct it and give it a completely consistent graph. On the right is a similar size but much more complex environment where it's got lots of narrow corridors that are self-similar, lots of chances for aliasing, lots of chances for false positives, yet with GNC we're able to have a consistent result and a strong global map there. To wrap up, I want to touch on a few high-level lessons and challenges that we found from working on SLAM in sub-T. On the left, firstly, we found that ground truth benchmarked data sets are super important. And so leveraging some of the ground truth point clouds from DARPA and some of our own testing, we developed 13 ground truth data sets that we're able to use to test, improve, and evaluate our algorithms. This is great, but it does have limitations. On the right, you see an attempt to do some parameter tuning. We're sweeping through 2 parameters, and each cell on the grid is the mean error on a given data set. And what is clear is that there's no trend. There's no real insight that we can get from this parameter exploration. And so we found that that's kind of one of the ongoing challenges, is how to adapt for parameters. Obviously, ideally, we don't have to tune parameters too much, but one of the things we're looking to in the research that's ongoing is how can we learn ways to adapt the parameters based on what's seen in the environment. With that, I'll hand over to the next team.
Now I will introduce the semantic understanding problem and solution. In the subject challenge, there are 10 times objects to explore. These 10 objects, called artifacts, represents the survivor's presence and rescue resources and require the multi-modality detection capabilities. Besides that, underground environments pose challenges in the lighting conditions and motion blur as robots walks on the bumpy ground, and the various scale of space and geometrics. During the operation, robots are facing the data limit challenge. At the end of the run, robots send data through the mesh network for the operator's review. The data volume should be below the network limits and the operator's cognitive low bandwidth. To handle various times of signals in the large scale of space, sensors need to have a big FOV and be compatible with the robot's payload under the size, weight, and power constraints. To tackle this problem, we have hardware and software solutions. On the hardware side, we have 7 types of sensors for the 10 artifacts signals, including color, thermal, carbon dioxide, Wi-Fi, Bluetooth, and sound. We also have software techniques to detect and recover from the sensor fault, so to keep the connections throughout the mission time. On the server side, we divide the data processing problem into visual and signal-based and build 2 pipelines. The visual pipeline takes in color and thermal images and run the data object detection algorithms on them. Scalability will further reduce the false positives. Each valid detection will be paired with a relative location and a global location and sent to the base station. Before showing that to the human operator, reconciliation will further group the data. Similarly, signal-based pipeline takes in carbon dioxide, Wi-Fi, Bluetooth, and sound reading into processors, and a valid detection above the threshold will pair with the global location. Then it's sent to the base station for the further review. Locality components are part of the early recall late precision stage of the detection pipeline. The goal of EARL is to reduce the false positives and optimize the data before being transmitted via the mesh network to the human operator under the constraint of GPU, network, and human cognitive load. At the beginning of the pipeline, robot sensors generate many images at high frequency. We sample them, for example, by selecting the least blurry images. These selected images will go into the detector, and the resulting detections will have low confidence at this point because we don't want to miss a true artifact. But of course, we need to take in the large amount of false positives. Scalability and the groupic techniques will reduce the majority of false positives. We will end up with 1 report for 1 object only. In this way, we achieve high precision before presenting the data to the human operator. These are the methods we use in each stage of EARL. We use a Plun YOLO version 5 medium model in TensorRT to achieve high detection rate at high image resolution. This allows us to detect small objects or objects from far and obtain a few observations for 1 object. At the scalability stage, we estimate the artifact's likelihood using color and size scores to filter the extreme outliers. A ranging filter groups the detections on board, as we only send 1 report for 1 detected object. The next stage is the reconciliation on the base station, which group the reports from different robots. The reports are sorted by scoreability, so the operator can optimize his time on the information with a higher certainty. For the signal-based artifact detected by 4 sensors, we use a similar technique, which is first to stream the detected signal strengths above the threshold and send to the base station, and visualize the signal strengths on the map in the user interface. Closer to the end of the mission, operator has the highest res mark on the map. He can click on the location on the map and generate a report to submit. Here, I would introduce how we optimize the visual report demonstration in the user interface. As I mentioned, ERP has the ranking step using scalability. In the user interface by default, the artifacts reports are sorted and shown in descending order of scalability. Through this quick access bar for the operator, he can work on the high confidence group first and the low confidence later. For each report, we concatenate 4 thumbnails to give the best observations for the operator under different criteria. These are including the low confidence, the brightness, the distance, and the blurriness. The result shows the effectiveness of object detection and report optimization under the constraints in the sub-T final event. We detected, localized, and report all the artifacts the robots encountered. Unfortunately, we missed the 1 file extinguisher because we submitted the report 2 seconds late. ERP shows the set of false positive pruning. The robot crew received almost 4 million color images. Over the stage in the ERP, we retained 164 unique objects for the operators to conform, and 9 within them are the true positives.
My name is David Fan, and I'll be covering Team CoSTAR's sub-T solution for traversability and motion planning. Subterranean environments are full of challenging terrain, which pose a wide array of dangers for mobile robots. Quantifying risk to robot health requires reasoning over uncertainties, which arise from noisy and sparse sensors. These uncertainties propagate into localization, mapping, and analysis of traversability and motion planning. This necessitates a framework which can reason about taking actions to reduce risk to the health and life of the robot. Traditionally, cost assessment for robot planning is deterministic, where a cost map of go versus no-go regions is constructed using rules-based geometric methods. In contrast, we wish to assess the probability that a planned path is safe, taking into account the uncertain distribution of geometric features generated from localization and mapping techniques. We wish to have a single parameter, alpha, between 0 and 1, to define a user-specified risk tolerance, where low alpha leads to an aggressive go, no-go behavior, and high alpha leads to a more conservative, risk-averse behavior, which takes uncertainties into account. This allows for adjusting the risks the robot is willing to take based on mission parameters such as mission time, robot type, communication bandwidth, and coordination with other robots. Our solution involves forward projecting uncertainty and quantifying risk through the construction of a risk-aware cost map. This cost map incorporates geometric uncertainties from LiDAR measurements and is generated using handcrafted features such as elevation, slope, step, and obstacle risks. This cost map is then used to compute risk-optimal, kinodynamically feasible paths using a constrained nonlinear MPC solver. This enables high-rate, real-time, safe, and agile navigation in constrained passages and varying slopes. Here we highlight the architecture of our method, which we name STEP, Stochastic Traversability Evaluation and Planning. Sensor inputs generate a state estimate and odometry. These measurements are merged temporally and filtered, followed by ground segmentation and elevation mapping. Our risk distribution analysis is applied to determine a multi-layer risk map. This map is then used by geometric and kinodynamic path planners to generate an optimal trajectory. This trajectory is fed to a tracking controller, which applies controls to the robot. Here we show results of our method operating in real time on Boston Dynamics Spot robot in Valentine Cave in Lava Beds National Monument in California. Traversability risks are assessed, encompassing slope, step, and obstacle risk. These risks are then aggregated into a single risk map. Then, an optimal trajectory is determined and tracked by the robot. This approach enables rapid and risk-aware exploration of challenging unstructured environments. Finally, here we show in more detail several situations to highlight our approach. In row A, the robot navigates around a small rock with an artifact placed on top of it. The rock is marked as risky and the robot navigates around it. In row B, the presence of slopes and a narrow passage to the side are marked as riskier than the wider passage in front of the robot. The robot prefers to explore the wider corridor first, reasoning about the risk of traversing through the narrow passage despite sparse sensor measurements. In row C, the robot reaches a dead end with rubble. Reasoning about the risks of traversing over the increasing slope and roughness of the rubble, the robot comes to a stop on the wider, smoother floor of the cave. These behaviors arise naturally and can be tuned with one parameter to prefer or avoid these types of risky situations.
My name is Sung Kim, and let me talk about the global planning and coverage solutions for Team CoSTAR. What is global planning? If we say traversability and local motion planning is about how to drive the robot safely, global planning is about where to drive the robot to discover new areas while ensuring the robot's safety. There are environmental and systematic constraints like 1 hour long exploration over kilometer scale environments, where the robots have imperfect sensing, control, and communication. The desired functionality for global planning is onboard computation, resilience to noise, respect to the robot dynamics, and adaptivity to diverse environmental characteristics. So we formalize this problem as a maximization of the coverage and minimization of the traversal risk at the same time for large-scale, unknown, and extreme environment exploration. The main ideas are in threefold: longer horizon planning on the uncertainty, compact environmental representation, and hierarchical structure to scale up to large problems. More precisely, we employed a PAM-DP solver for simultaneous optimization of input gain and action costs. And we devised a scalable semantic encoding structure, which is called IRMs, or information roadmaps. And we leverage some local global structure so that we can pursue local optimality and global complementary at the same time. So we call this architecture as Pilgrim, probabilistic local and global reasoning on information roadmaps. So this module is given a risk map, which is a local occupancy, and postgraph, global robot trajectory, and it is to generate coverage path so that the local motion planner to follow it. It has two main functions, belief representation and value function learning. So in a hierarchical structure, we maintain global and local IRMs, and we solve for global and local coverage plannings. If we see this in a receding horizon planning fashion, we also perform some receding horizon policy reconciliation so that we can balance between the policy consistency and policy resiliency to sudden findings in the environment. To illustrate our solution a little more in detail, this is some hierarchical belief representation we use. So given a postgraph and the risk map, we maintain local IRM, which is rolling window semantic representation, and global IRM, which is a graph structure, sparse information in a semantic fashion. And for local and global planning, we use PAM-HDP algorithm, which leverages ensemble of heuristics and some our novel idea about front-loaded input gain for orient tiering so that we can discount some distant rewards in a very large scale. And then on top of those, we have some meta-level modules that perform some policy feasibility testing and switches between the global and local policies. And also, we capture some environmental characteristics such as spaciousness, and then we adapt our hyperparameters for lower level coverage plannings. To share some design philosophy at a very high level, we design our local motion planning to be a bit pessimistic so that we can guarantee the robot's safety. But for local coverage planning, we rather set it to be optimistic so that we don't miss some important but small openings for exploration. For global IRM level, we want to be conservative and try to balance between the two. And then the reason for that is decision-making at global IRM level is very big. So if we have some false positives or negatives, the decision will be very suboptimal. For local coverage planning, the main focus is on performance, so, such as the don't want the robot to stop and go intermittently while exploring. And we want to drive the robot in the middle of the corridor if possible. For global coverage planning, the main key is about the scalability, so that we can think about like a hundreds or kilometer away, hundreds meter or kilometer away frontiers, and then whether we decide just continue local exploration here or move to large openings we had left before. And at the meta level, the main key is the adaptability about the environment and then some dynamic changes of the our understanding about the environment. As for the results, there are some key keywords for our solution, such as resiliency, adaptivity, risk-aware, scalable, and near optimal and complete functionalities. Now, unfortunately, I don't have enough time to go through all individual experiments results, but at a high level, we can see on the left bottom, the robot is exploring very tight space, but immediately it is connected to wide opening, and it changes hyperparameter for coverage, and it explores that wide space in a nice way. And very large scale, like the middle bottom, the overall traversal distance is like 1.5 kilometer, but it continues exploring while maintaining the overall understanding about the global coverage, and it tries to locally complete the coverage. And in the middle top video, you can see the lava tube is very rough, extreme terrain, but we negotiate with the traversal risk and the coverage regain, and then safely continue exploration over the mission. So currently we are working on a set of papers to present our work on global planning. So please stay tuned, and we'll be happy to answer any questions offline. Thank you.
Now we'll spend a few minutes discussing our multi-robot networking. Subterranean environments pose several challenges for communication. Branches make wired solutions difficult to implement, but wireless communication deals with lossy links and suffers over large distances. Obstacles in the environment prevent line-of-sight communication and can severely attenuate radio signals. Despite these challenges, we want an architecture that can meet the needs of multi-robot exploration. These include high throughput, low latency, large effective communication ranges, reliable data transfer, and cooperation between robots via mesh networking. Our communication architecture seeks to extend the effective communication range from the base station and enable high bandwidth data transfer over large distances. Our approach can be thought of in three parts, each of which will be discussed in additional detail. The network architecture itself, as shown here, which leverages droppable software-defined radios to build up a mesh network. The communication modeling and communication-aware autonomy, which allows our robots to make intelligent decisions, for example, where to drop these nodes. And distinct protocols for reliable and low latency data transfer, which meet the needs of mission-critical data and time-sensitive data, respectively. Each of our robots is equipped with a Silvus MIMO radio and Silvus Layer 2 and 3 protocol implementations for multi-hop routing. Each spot can also carry and deploy an additional 2 droppable radios via custom hardware, as shown in this video taken during the competition. Each Husky can carry and deploy an additional 6 droppable radios, as shown on the bottom right. Deploying droppable nodes lets us improve the signal quality of the surrounding environment, which we capture in the communication environment state. The key metric here is signal to noise ratio, or SNR, to the closest static node. Each robot maintains the collective communication environment state in a roadmap, as shown here. Each robot also monitors the amount of mission-critical data it has which needs to be transferred, i.e. the buffer sizes. The key metric here is buffer size, and whether it is increasing or decreasing gives insight into whether the network is congested. Therefore, we call this the communication network state. The environment state and network state together inform decision-making. As the SNR falls below a desired threshold, robots deploy additional communication nodes. So the picture on the left here shows 12 comm nodes which were dropped during field testing. And when the buffer sizes become too large, the robot returns to areas with measured or predicted values of good connectivity. The right picture here shows connectivity prediction, which is useful when new nodes are dropped and old measurements have become outdated. Given that we expect robots to leave and return to connectivity, it is especially important that our communication software architecture is designed to handle reconnection. While we rely on ROS1 for inter-process communication on a single robot or on the base, it is not well suited for multi-robot operations. ROS2 provides solutions for neighbor discovery and is sufficient for transferring unreliable data, for example, the robot status. This is data that should be sent with low latency, but doesn't need to be retransmitted if it's not received. For reliable data, for example, artifact reports, we implemented custom modules based on multi-master FKIE. And our implementation provides queue size monitoring, acknowledgements, and rate limiting flow control to efficiently use the bandwidth available. The result is that our robots can autonomously deploy a communication network, providing an effective range of hundreds of meters as shown on the left. And through a combination of improved signal quality and carefully designed protocols, the human supervisor can reliably receive artifact reports and other critical data.
Now I will give you an overview of our multi-robot mission autonomy component. Multi-robot coordination is a large open problem with a lot of challenges. In the context of double sub-T, some of the challenges include coordination of a large number of robots, limited deployment time, especially for large teams of robots, parsing and understanding high volumes of data come from those robots in dealing with dynamic environment with intermittent communication. The goal here is to build algorithms to maximize mission success probability while dispatching heterogeneous capability to different parts of the environment based on the mission specification and based on the state of the mission at each point in time. As we will see in the next slides, we address these challenges by developing algorithms for assistive operation and automated robot deployment with task planning for efficient operation with advanced UI and for resilient adaptive robot autonomy with a autopilot. In our operations architecture, the operator is supported by an autonomous assistant called Copilot before and during each run. Copilot is extremely powerful, allowing for flexible mission task planning and execution, enabling the operator to manage a large number of autonomous robots in a mission. It's worth mentioning that we identified that a single operator has a really hard time managing a team of more than 3 robots without such assistant support. With Copilot being as robust as it is, allowing for both pre-mission task planning and in-mission planning, implementing it within the user interface we developed, we are able to make it cognitive coherent, reduce context switching, and increase parallelism for the human operator. The user interface with Copilot integrated further facilitates the ability to operate 8 or more robots in one mission, while allowing for full trust in the onboard robot autonomy. Operator experience was originally driven through various applications on a per task basis, with the majority of time spent in terminals. We designed and developed a single integrated web-based user interface, especially for the final event, to tie the capability of the various systems together. We integrate the capability of Copilot for our deployment automation and monitoring, the functionality of Office through a custom and high-performance iterative 3D visualization, the data from the real-time status of the robot's team health, and the artifact reporting. Having one cohesive experience enable efficient monitoring of 8+ robots set up in expensive environments. prevented the operator from unnecessary context and application switching, and ultimately helped us to achieve our goals of decreasing the operator cognitive workload and increase situational awareness. Creating this integrated user interface allowed us to create more natural interactions for the operator. For example, click on a robot and see it within the 3D view, or command it to drop a communication node, submitting an artifact report while still being aware of the environment surrounding and the robot's health, or without asking the operator to juggle separate UIs or applications. Here we have a closer look at the UI modules. In A, robot-specific copilot tasks are conveniently anchored alongside with the robot status. In B, the operator is able to speedily navigate through artifact detection depending on their confidence. And overall, we see the operator can see the status of the robot team while also be able to command them within the 3D view. At the beginning of our subtlety journey, our operator had to keep in mind all the procedures and tasks needed to deploy each and every robot. This is a time-consuming and error-prone process, which we automated by introducing the concept of our autonomy copilot. We actively schedule and reschedule between 15 to 20 tasks per robot, execute them autonomously, and notify our operator if actions are required. This leads to reduced workload on the operator side and a very efficient deployment of large robot teams. This approach also increased the resilience of the system by allowing flexible task execution in case of the operator change their strategy or when the robot or sensor failures occur. The autopilot is responsible for the onboard autonomy and decision-making. The JPL traces the mission executive running or each robot that executes the mission specified in the BPMN and control its progress in a manner similar to a finite state machine, and also accepts human operator commands. Each block of the BPMN corresponds to a behavior that the robot can execute. We have four main types of behaviors. The first one is exploration within the red block, and it's the nominal behavior that we want the robot to have active as much as possible. The second one within the green block corresponds to the monitors that, based on the system health and external requests, evaluates the need for executing specific sequence of responsible behavior, which is the third category of behavior that is showing in the yellow block. Example of those drop communication node, climb the stairs, fall and stuck recovery. The fourth type corresponds to the return to communication that we use to warn the operator of a system malfunction. There is another return to communication behavior that is used to report data, but this is embedded in the exploration behavior. The combination of these autonomy capability, both on the base station and on board each robot, allowed us to clearly improve our operations overall and enabled single supervised operation with a large number of robots quite feasibly. Here are some interesting performance highlights on that front. It allows us to efficiently deploy and operate 6 ground and 2 aerial robots and increase the capability to greater than 8 robots simultaneously. Copilot automation reduced deployment time to less than 1 minute per robot. And in our field tests, we reached for single robot autonomy for up to 1.7 kilometers while being most of the time out of comms.
Okay, so this was an overview of some of the modules that come together and create our Nebula autonomy framework that we used in DARPA Subterranean Challenge. You can find more details about these methods in the papers listed here. Also, you can find more details and videos about these solutions and our more up-to-date information on our website listed up here. With this overview, let's now look at some of the core lessons we have learned in this competition. There has been a huge number of lessons, and this has been an amazing experience for our team. Number one lesson is overall as a community, we still have a lot of work to do along the lines of subterranean challenge. Even in the best scenarios, the best teams in these competitions, we roughly scored only half of the points. So that shows we still need to do work in research side, on the algorithmic side, as well as reliability of these systems to be able to deploy them and they efficiently operate and accomplish the missions. But more specifically, some of the lessons learned are for our team are listed here. Number one is heterogeneous robot teams are highly capable. And there's a lot of open problems in that domain, how to handle the coordination, how to design these teams, how to select best skills. But like a human team where different team members have different skills and together they accomplish a mission, we saw in this challenge that most of the team came to the competition with multiple robots with different skills, and they together in a collaborative way try to handle and address the difficulties of this mission. A second big lesson was that it's very critical to have good and principled approaches to manage the trade-off between reliability of the systems as well as developing advanced autonomy capabilities. In one hand, it's really important to do research to develop the next generation autonomy solution and advance our algorithms. And on the other hand, it's really critical that test and integrate these systems repeatedly, increase their reliability, and one doesn't work without the other one. So considering these two together in the design is really important. Human-centered and communication-aware autonomy. Over the last few years, one big lesson for us was that it's better and it's important to take into account human cognitive load and constraints that come from the human supervision into autonomy from day one, rather than developing autonomy and then introducing human to the mission. Similarly, with communication, it's really important to look at the constraints and opportunities and challenges that comes with the communication solution and bake that into autonomy from day one, so that you have a calm, aware autonomy and maximize the chances of accomplishing a successful mission. Next item is semantic metric planning. While geometric mapping and planning can lead to a lot of intelligent behaviors, for more complex next generation systems, it is important to understand the environment semantically and have an idea of what is the stairs, what's door, what's a window, and what are the topological information about the environment, and plan based on those to enable higher levels of autonomy and intelligence. Off-road traversability is very hard. We saw over and over that it's really difficult to analyze the terrain and enable a smooth and robust traverse over the terrain. And specifically when there are unknowns in the environment, it's really important to take into account uncertainty to enable more capable off-road traversability, and to make sure that by taking that uncertainty into account, the system is collecting enough perceptual information before attempting to traverse the hard elements of the course. Finally, I want to highlight some of our new projects that we just started and some of our future directions that are aligned with the lessons learned that I was talking about. The first one is the RACER project that focuses on off-road traversability for passenger size self-driving cars. The bottom video, of course, is a dream. This is there's a driver here, but we have the exact same vehicle that you can see at top, fully loaded by sensors and computers. And the idea is, and the goal is, to go faster and faster over no road terrains in off-road setting, for this purpose, we are actually leveraging a lot of what we have done in DARPA Subtraining Challenge, and in all these projects, we are leveraging the autonomy nebula autonomy solution that we created at the DARPA Sub-T. The second project is the Braille project that focuses on technology development and demonstration towards a future potential mission to Martian caves. Basically, in this project, we take the robots to Mars analog caves, and leveraging a lot of what we have learned in DARPA Subtraining Challenge from our efforts and from other teams to demonstrate to NASA and the space sector that these technologies are maturing, and these might pave the way for a mission to Martian caves in the next decade. Navigation and coordination between aerial systems and ground robots, which was an important problem that DARPA Subtraining Challenge, is informing a lot of our efforts towards developing algorithms for prototype Mars helicopter and rover coordination navigation. And finally, we just started a project on semantic-based reinforcement learning for autonomous robot navigation in unknown environments. And many of these are thanks to the technology developments that occurred in DARPA Subtraining Challenge. But finally, above all of this, I want to highlight that the best part of this challenge has been the opportunity to work with this incredible team of researchers and students from all over the world, either in person or remotely. And for that, I'm very thankful for DARPA Subtraining Challenge to create such an opportunity that these teams come together and create these technologies and learn from each other, and also across different teams learn from other researchers and students in other teams participating in this challenge. So with that, I want to thank everybody for your attention. If you have any questions for us or want to follow up, you can find more information on our team website or send us emails. Thank you.